Hi, everybody. Welcome to Lecture 3 for Phil 2002 Logic, How to Defeat Your Foes with Reasoning. Before we get started, I'm going to just give you a little bit of an overview of what we've had a look at so far. So in the first lecture, I was introducing you to the idea behind investigating logic and logical reasoning more generally. What we're trying to do is trying to understand when an argument can be good and when an argument can be bad. And what we saw is that there are two tests that an argument needs to pass in order for an argument to be bad. In order for an argument to be good. So in order for an argument to be good, it has to be valid, which means that it's impossible for the premises to be true and the conclusion false. And the argument to pass the second test has to be sound, which means that, as a matter of fact, the premises are true. One of the key things to understand about validity is that it doesn't require the premises to be true. All it says is that if the premises are true, then the conclusion has to be true as well. It's soundness that requires validity and then the truth of the premises as well. What we wanted to do with our concept of validity is come up with a foolproof method that we can use to work out when an argument is valid or invalid. We want to know when someone's putting forward an argument whether it has the right kind of structure in order for us to be able to say that it's a good argument. And in order to develop this foolproof method, what we've started to do is develop a basic language for translating complex arguments in English into something very, very simple. And the idea behind this translation exercise is to try and focus in on the logical structure of the English sentence so that we can give a sort of pared down, simplified account of that structure and then giving us the ability to say interesting things about the structure that we've developed. So what we saw was that our basic language was able to sort of map the very simple structure of certain straightforward arguments. Ultimately, what we want to be able to do is use this representational system, this very basic language, to be able to map and model very, very complex arguments and indeed to be able to work out whether or not those complex arguments are good or bad. What I'm going to be doing today is looking at the semantics of the language that we've developed. So far, I've just given you a syntax. And a syntax is just a way of understanding the symbols that appear in the language and how to write those symbols out in a correct and coherent manner. In much the same way that you might have a syntactic structure in English, so too does our basic language, the first logical system that I've introduced you to, propositional logic, so too does that have a basic syntactic structure. But without a semantics, without an understanding of what the meaning of the symbols inside our language are, it's very difficult to take the language very far, and indeed it's very difficult to even start to get a sense of what validity might mean or how to test for validity once we've translated things into this language. If you just translate an English sentence into this language and then say nothing else, we have no way of knowing what the sort of translation ultimately means, except for its relationship to the English. But ultimately what we want to do is give a particular account of the meaning of the symbols inside our language, and that's what we'll be having a look at today. Okay, remember this focus. What we're trying to do is come up with a general foolproof method for determining whether or not an argument is valid. And we're going to use this basic language in order to get us there. We've got one half of the language, the syntax. Now we're going to drop the semantics in there. And together, in the next lecture, I'll show you how to bring those into understanding the validity of an argument. Okay, let's recall the syntax of our language. In the language, we have basic propositional letters, and these propositional letters, remember, are being used to represent basic propositions. A basic proposition is any proposition that doesn't have other propositions as parts, which is to say, if you've got a proposition and you can't take things away from it in order to get to something that is also a proposition, i.e. also something that can be true or false, then you've got a basic proposition. If, however, you've got a proposition where you can take things away from it, you can take parts out of it and still end up with something that can be true or false on its own, then what you've got is a compound or molecular proposition. And what we do with our basic syntactic scheme for propositional logic is we represent all of our basic propositions using these capital sentential letters. What we then have is 5 connectives in order to represent the logical joints that we find in English that we want to analyze inside our logical language. First of all, we've got this V symbol, and that represents the disjunction, either A or B. We've got this wedge symbol, which represents the conjunction, A and B. We've got this negation, which represents it not being the case. So if it's raining and I want to say it's not raining, then I'll add a negation to that basic proposition. We've got this conditional, which expresses an if-then relationship between two things. And we've got the biconditional relationship, which expresses a relationship of standing or falling together. Two things have to be true together or false together when they stand in this biconditional relationship. And then we've got the parentheses, and we use the parentheses in order to disambiguate sentences inside the language. And the way that we define the syntax was using this recursive structure. And this recursive structure, the beauty of it is that we can use it for arbitrarily complex statements inside our propositional logic. Okay, a note on translation. Remember what we were doing last time was taking sentences in English or arguments in English and translating them into this basic system where we've got now a sense of what is sort of syntactically acceptable within that system. But it's very important to note that our goal is not to take everything inside the English language or everything inside an English sentence and translate all of that into our logical language. The whole point behind a propositional logic or behind any logical system is to abstract away from irrelevant information that might be sitting inside the language that we might be using for linguistic or communicative purposes so that we can just focus in on the logical structure of what it is that someone's saying so that we can analyze that logical structure. So, for instance, there are lots of things that we do or say in English that have nothing to do with logical structure. So, for instance, if I emphasize something in English by saying, "You're really, really happy," then logically speaking, I might not be saying anything over and above, "You're happy." But the emphasis is being used for linguistic or communicative effect. Of course, in this case, it might also be some kind of adverbial modifier. I might actually be saying, look, there's more happiness than you might think here. But the sort of emphasis, the tone of what I'm saying, I'm really, really happy, that tone is not actually adding anything that we want to model inside our logical system. We want to keep our logical system away from things like emphasis, intonation, connotation, those sorts of aspects so that we can just focus on the pure reasoning component of what it is that someone's saying. All right. What we need in order to develop our foolproof method is a semantics. And a semantics for any language is just an interpretation of that language. It's just an account of the meaning of the words or symbols or whatever it is that that language is composed of. So for instance, if you go to a dictionary and you look up a word, what you're doing is you're trying to get a grip on the semantics of that word embedded within the language. It's very difficult, or it can be very difficult, to give a complete semantic system for a complex language like English. Fortunately, our language, our propositional logic, is so simple that providing a semantics for it is actually quite straightforward. As we go through the course, we'll be looking at some different types of semantic systems. Some of these semantic systems are used extensively in linguistics and computer science and outside of philosophy or logic or reasoning. And of course, we use these semantic systems in an everyday level to understand each other when we communicate. Of course, the semantic system that I'll be showing you is much simpler than the kinds of semantic systems that you already carry around inside your head. So, if we are able to understand each other in an ordinary way when we speak English, we're already doing something much more complicated than the very basic semantic system that we'll be looking at. What we need for our semantics in particular is something that can speak to the truth or falsity of the types of claims that we have inside our language. Why are we interested in truth or falsity? We'll come back to what it is that we're trying to do. We're trying to understand whether an argument is valid or not. And in order to work out whether or not an argument is valid or not, we need to try and work out whether it's impossible for the premises to be true and the conclusion false. But in order to do that, we need to be able to have some way of assigning what's called a truth value or a semantic value to the premises and to the conclusion. So we need some way of determining whether or not a premise is true or whether it's false, or at least the conditions under which it would be true or it would be false. And that's what the semantics for propositional logic is going to do. What it's going to do is going to tell us for each of the sentences inside our language, the conditions under which that sentence will be true or false. That's not completely true. What the semantics is really in the business of doing is looking at the compound or molecular propositions. For basic propositions, if you want to know whether one of those propositions is true or false, for the most part what you have to do is you have to go out into the world and you have to try and analyze the the conditions under which that sentence might yield truth or falsity by carrying out some empirical investigation or looking at things in the world. What we're going to focus on is the sort of relationship, the semantic relationship between the basic propositions and the compound propositions. And that semantic relationship is actually going to turn out to be really important for understanding the validity of an argument and indeed ultimately the soundness, although we won't be looking too much at soundness. All right. Another way of putting what I've just said is that the semantics for basic propositions is actually very straightforward. And it's not really very different to the kind of semantics for basic propositions or semantics for propositions more generally that you might find in the English language. For a basic proposition inside propositional logic, remember this is a proposition that's represented by a single capital letter. Whether or not that proposition is true or false depends upon how the world is. So for instance, if I take the proposition, it is raining, and I assign that the propositional letter A, and I want to know when is that proposition true or false, I have to go out into the world and I have to look, I have to see whether or not it's raining. So the world sort of has to tell me how it is that that proposition stands with respect to its truth or falsity. And that's the same is true for all basic propositions. So that makes basic propositions, in some sense, the sorts of things that we're going to be understanding when we do things outside of philosophy. When you might do science or linguistics or history or something like that, you'll be looking at the truth values of these propositions. Our focus here is going to be looking at the truth values or the more complex conditions for compound or complex propositions that we might be building out of some of these basic propositions. All right, so let's focus in on the compound propositions. For basic propositions, a basic proposition, whether or not it's true or false, depends upon how the world is. For a compound proposition depends for its truth or falsity on the basic propositions that make it up. So remember, a compound proposition will be some basic propositions with one of our connectives connecting those propositions together. So for instance, if I have the compound proposition, it is raining and it is windy, that compound proposition has as parts the basic propositions, it is raining, and the proposition, it is windy, and they're connected by the and connective, which is that wedge connection that we saw in the syntax. What we want to say for our compound propositions, for all compound propositions, and indeed for arbitrarily complex compound propositions, whether or not those propositions are true depends on the basic propositions that make them up and the relationships that they stand in as specified by those logical connectives. What we're going to do now is we're going to go through each of our connectives and we're going to come up with a set of conditions under which that proposition is true or false. Now, what we'll be doing is very, very particular to our understanding of validity, and so it's worth pausing to just reflect a little bit on what it is that we're going to be looking at as we go forward. What I'm interested in is sort of providing a map of all of the possible situations under which a proposition might be true or false. Why am I interested in providing a map of that kind? Well, when I'm trying to understand validity, I'm trying to work out whether it's possible for the premises to be true and the conclusion false. And so what I need to do for the premises and for the conclusion of any given argument is provide a kind of map of all of the possibilities to see whether or not within that map there is some place where the propositions are true and the conclusion false. If I can look at one of these maps, and we'll be building some of these maps as we go, if I can look at one of these maps and just see that there is some possibility in which premises are true and conclusion false, then I know immediately that the argument is invalid. And if I can't see that possibility, if there is no such possibility, then I know immediately that the argument is valid. We'll be looking in more detail at validity and invalidity later on. For now, the thing to focus on is that when I'm looking at the conditions under which a compound or complex or molecular proposition is true, what I'm trying to do is look at all of the possible situations under which that proposition might be true or false. And now the possible situations that I'm interested in are situations with respect to the basic proposition. So take a given basic proposition. Consider the proposition, it is raining. What are the possible situations that the world could be in with respect to that proposition? On the face of it, it seems like there's just two. On the one hand, the world could be such that it is in fact raining. So that would be one possibility. Another possibility could be that the world is such that it's not raining, and that would be the other possibility. And that seems to exhaust the options. Either the world is such that it's raining, or it's such that it's not raining. There are no other options, and so we've mapped fully our possibility space for that basic proposition. So what we're going to do is we're going to have a sort of possibility map for our basic propositions, and then we're going to look at our compound propositions in relationship to that basic possibility map. All right. We'll be looking at some pictures and some diagrams of this as we go, so which will help to make it a little bit more clearer and a little bit more concrete. Okay, these possibility maps that I've been talking about are what we call truth tables, at least with respect to this basic propositional logic. A truth table is, very roughly, a way of mapping out all of the possible situations under which a basic proposition is true or false, and then with respect to a given compound proposition, whether that compound proposition is true or false with respect to that basic proposition. Okay, so have a look at this basic proposition. The basic proposition is that cats are robots in disguise. It looks like there are just two options with respect to that basic proposition. On the one hand, it might be the case that cats are robots in disguise is true. On the other hand, it might be the case that cats are robots in disguise is false, right? So we've got these two possibilities. Now consider the compound proposition that cats are not robots in disguise. It seems right to say that when cats are robots in disguise is true, the compound proposition, cats are not robots in disguise, is false. Similarly, when cats are robots in disguise is false, that basic proposition is false, it seems right to say that cats are not robots in disguise is true. Okay, so what we're doing here is you can think of this as taking a basic proposition with a sort of given possibility assigned to it, feeding it into some box that modifies the proposition in terms of some connection or some relationship, like a negation or an and or an or, and that will then spit out some result. So if we like, we can draw a picture of this to get a better sense of how it works. All right, so let's suppose that we've got a box. All right. Now into this box, what we're going to do is feed in possibilities. Now we're looking at the proposition that cats are robots in disguise, right? That is our proposition. Okay, so there's our basic proposition. And what we know is that there are two possibilities for this basic proposition. We can have one possibility where that proposition is true, and we can have another possibility where that proposition is false. Okay, so there are our possibilities. And what we're going to do is we're going to take these possibilities, and these are ways, you can sort of think of them as ways that you can imagine the world being. We're going to take these possibilities and we're going to feed them into this box. All right, now what is this box? Well, this box is the negation box. And what does that mean? Well, what it does is it takes in propositions and then it churns around and then it spits out something with respect to the negation of those propositions. So, for instance, when we take in that A is true, what this box spits out is that not A is false, right? So it takes that basic proposition, modifies it with the negation, and then spits out an answer. And when we take in that A is false, what the box does is it spits out that not A is true, all right? Now, for those of you who have done mathematics before or linguistics before, another way of thinking about what this is that it's a function. And if you've not done mathematics in terms of functions before or linguistics with respect to functions before, that's fine. All you need to know about a function is that it's something that takes in inputs and yields outputs of a certain kind. And the negation is a certain kind of function. In this case, what the negation does is it takes in possibilities or possible truth values for a basic proposition and then operates on them, and then it spits out some value for a negated proposition, right? So it yields an input. It yields an input based on some output. All right, what this actually is, this sort of diagram that I've drawn, it's actually a map of, on the one hand, the possibilities for the basic proposition. We've got those basic propositions mapped here. And then it's a map of the possibilities for the compound proposition as a function of the possibilities of the basic proposition. So that is to say that we get some account of the possibilities for the compound proposition in terms of the values for this basic proposition that we're feeding into the function, or feeding into this negation box. All right? Okay, so this is one way of representing the possibility space. As you can see, it's a little bit messy, it's a little bit complicated. We have to draw a diagram and sort of wave our hands a lot in order to get the idea across. There's a simpler way to do it, and the simpler way to do it is actually to represent this information in a truth table. So let's have a look at a truth table. So what we can do is we can take the information that we were looking at just a moment ago about cats being robots in disguise. We've got that as a basic claim, and then we've got this non-basic claim which is involving our not operator, and we feed that information from the basic claim into the not operator, and we get some result out. And what we can do is we can represent that entire box that I just drew as this truth table here. And what the beauty of this is that it sort of abstracts away from the details of cats and so on in order to just give us a very general account of what the negation does. So if I have a basic proposition A and it's true, and I add a negation to it, sorry, that should be this thing. We need it should be the angle bracket. Wrong symbol, there we go. Not A, so if I take not A like that, and I feed it into I feed this A into that not A, and if the A is true, then it's going to spit out a false, and if the A is false, then it's going to spit out a true. Right, so this is just another way of representing the very same information that we were looking at a moment ago. Now, it's quite easy to see how this works for the negation. But once you see how it works for the negation, it's not super hard to see how it's going to work for other propositions as well. The negation we can use as a kind of model for thinking about other cases. For each of these truth tables, what we see is that we've got some basic propositions over here. So here's our sort of initial statement of the possibilities for the proposition or propositions that we're interested in. And then we see how those possibilities get transformed in terms of the negation or in terms of some other operation such as an and or an or the if-then, the conditional, and we get results being spat out. And what we have here is a map of all of the possible situations under which this compound proposition is true or false in terms of that basic proposition. And again, remember, it's the map of the possibilities, it's the map of the possibilities that we want. Okay, now we can produce one of these truth tables for each of our non-basic claims. So for each of the connectives inside this propositional logic, whether we're using and or if-then or the bicondition or whatever, we can produce one of these truth tables. And by the end of this lecture, we'll have seen all of the different truth tables that you can have for these particular connectives that we're interested in inside our basic propositional logic. But before we have a look at these other truth tables, what we have to do is we have to step back a little bit and think about the notion of possibility. So when we're dealing with just one claim, when we're just looking at A, say, and we're thinking, okay, what are the possible situations under which A is true or false, then we just seem to have two. Either A could be true or A could be false. But suppose we have a second proposition. If we have a second proposition, then we increase the number of possibilities that there are. And as we add more propositions, we keep increasing the number of possibilities. Why? Well, look, we can have a possibility, once we've got sort of two propositions in the picture, A and B, we can have the possibility of them both being true and them both being false, so we can sort of have those initial possibilities. But we can also vary combinatorially the relationship between these two propositions. So we can have a case where A is true and B is false, and we can have a case where A is false and B is true, right? So that gives us 4 possibilities to work with. And importantly, what you can see is that these are all of the possible options. There are no other ways for these propositions to be with respect to each other and with respect to a possibility. So there's a possibility where they're both true, there's a possibility where they're both false, there's a possibility where one is true and the other is false, and there's a possibility where the other is false and the one is true, right? So we get all of these different possibilities. And when we're looking at our compound propositions that involve more than one proposition, and some of those compound propositions did, like the and the or and the conditional, what we have to do is we have to set up our possibility space in a more complicated way. We have to have as many possibilities as there are basic propositions entering into the connective that we're looking at, right? So if we're looking at something like A and B, then because we've got two basic propositions, namely A and B, inside that compound proposition, our possibility space for setting up that proposition is going to have these 4 possibilities in it, because we want to map all of the possible ways that A and B can be together. All right, we'll look at some more complex possibility spaces later on. As you add more and more propositions, you get more and more possibilities that you have to deal with, and later on we're going to try and find a useful tool for navigating our way through all of these possibilities without having to go through and look at each one individually. But for now, we're just going to focus on the case where we've just got 4 possibilities, because that's going to be enough for us to set up the semantics for our basic propositional language. Okay, so just to give you a concrete example of what I just said, suppose that A is it is raining outside and B is cats are robots in disguise, and now consider what are the possible ways that the world can be with respect to these 2 propositions. Well, first of all, it could be the case that it is raining outside and cats are robots in disguise. Second, it could be that it's raining outside but cats are not robots in disguise. Third, it could be that it's not raining outside but cats are robots in disguise. And fourth, it could be that it's neither the case that cats are robots in disguise and nor is it the case that it is raining outside, right? So both propositions could be false. And again, it doesn't seem to be any other options. There doesn't seem to be any other way the world could be with respect to these 2 propositions. All right, so what we can do is we can represent that information inside this sort of setup for the truth table. What we do here is we just represent all of the possibilities that we're ultimately going to be interested in, and we get this neat little 4-line matrix where we have all of the possible relationships between A and B mapped out. Now, if you want to set up one of these truth tables yourself, it's very simple to do. You just start with your 2 propositions like this, and the number of lines in the truth table is 2 to the power of n, where n is the number of basic propositions. So if I've got 2 basic propositions, then the number of lines in the truth table is going to be 2 times 2, which is equal to 4. That's a 4, trust me. There we go. Okay, 2 times 2 equals 4, and so that's going to give us 4 lines in the truth table. If I have 3 basic propositions, then it's going to be 2 to the power of 3, which is going to be 8, and so on. They get big very quickly, which is something that we'll return to later on. Now, in order to get all of the possibilities out, I can just mechanically go like this. I start with the first column, I write TF, TF, and then as I go down the second column, I go TT, FF, and that gets me all 4 distinct possibilities. A couple of things to remember: the number of lines in a truth table is always even because you're using a function as a power, you're using an exponent of 2, so you're never going to have an odd number of lines in your truth table, at least with respect to these kinds of 2-place connectives. And the other thing to note is that you don't want any repeats in this matrix, right? So you don't want there to be 2 lines with respect to just when you've just got 2 propositions where both A and B are true together. If I had a third proposition C, then you would get repeats, but with just A and B, you want to make sure that each of those 4 lines is unique. It provides a unique possibility, and you haven't left any possibilities out, and you haven't repeated possibilities either. Okay, so now that we've got our basic possibility matrix set up for our basic propositions when we've got more than one, we've got 2 propositions, we've got these 4 lines, what we can do is we can actually start to do what we did for not for the other compound propositions that we have in our language. So our compound propositions involve things like and or, and the conditional and the biconditional, the if-then and the double arrow. And what we're going to do is we're going to build a truth table for each of those different connectives, where that truth table will tell us the sort of possible situations under which the relevant proposition is true or false. It'll tell us when those propositions get to be true as a function of the basic propositions that we feed in. All right, so let's start with and, the easiest one, the conjunction. So consider the following conjunction: it is raining outside and cats are robots in disguise. What we want to know is, when is this proposition true? What would possibly make this proposition true? The compound proposition, that is. It seems to be the case that the compound proposition is true just when both of the two things connected by that and are true. So when it is raining outside and cats are robots in disguise, then that compound proposition, it's raining outside and cats are robots in disguise, gets to be true, and it's false in all of the other situations. So when it's raining outside but cats aren't robots in disguise, then the conjunction is false. When it's raining outside is false and cats are robots in disguise is true, then the conjunction is false because you don't have both things being true. And when neither of the things is true, then again, you get the case that the conjunction is false. So just as with the not, we can think of this in terms of a box. All right. So here we've got a box that we're going to feed information in. This time it's the AND box. And what we're going to be doing is we're going to be feeding in pairs of values for A and B. So if A is, we've got all our 4 pairs of values that we started with in the matrix at the beginning. So these are all of the possibilities. Right, so we've got our 4 possibilities, and all of those are going to be fed into this AND box. And what happens is that box is going to shake around and it's going to spit out results for each of the things that we feed in. So when we feed in that A is true and that B is true, it spits out that A and B is true. Oops. Have to start again, hang on. So we're feeding in A is true, B is true, A is true, B is false, A is false, B is true, A is false, B is false. So we've got those 4 pieces of information, we're going to feed them all in, and the box is going to spit around, and when you feed in that A is true and that B is true, then the conjunction is true. And when you feed in that A is true and B is false, then it's going to yield the result that the conjunction is false. And when you feed in that A is false and that B is true, it's going to yield the result that the conjunction is false. And when you feed in the information that both of them are false, then it's going to yield that the conjunction is false as well. Right, so what we get is 4 values being yielded by our box. And those 4 values represent the possible situations under which the conjunction can be true or false in terms of the values of the basic propositions that we're interested in. Again, writing this is messy. You have to draw one of those diagrams, but what we can do is we can just fit this into a table in a nice, neat way like this. Sorry, this should be the wedge. There we go. There we go. So it's the conjunction. And what we see is that when A is true and B is true, then the conjunction is true, but it's false in all the other situations. And this is our possibility map for that conjunctive proposition, which is what we want. Okay. Next, we're going to look at OR. Consider the following compound proposition. Either it is raining outside or it is sunny outside. When is that proposition true? Well, it seems to be true either when it's raining outside, or when it's sunny outside, or when both are true. Now remember when I introduced the disjunction to you, the OR, in the previous lectures, I mentioned this distinction between an inclusive and exclusive disjunction. And this OR that I've got written here is the inclusive disjunction. So this says that the inclusive disjunction is true when one side of the disjunction is true, so when it's raining outside or when it's sunny outside, but it's also true when both are true. So it's not representing anything like mutual exclusion when the two things can't be true together. We could, if we wanted to, represent the mutually exclusive case, but we're not going to be looking at that in the space of this course. Okay, so what we're going to do is we're going to feed in our information, and again we're feeding in the possibility space for the basic propositions that we've got. On the left here we've got the basic proposition, it is raining outside, and on the right here we've got the basic proposition, it is sunny outside, and then in the matrix we've got all of the possible combinations for these two propositions. So we've got it is raining outside is true, it is sunny outside is true, and so on for each of the different options. Now importantly, there's only one situation under which the disjunction will turn out to be false, and that is when both sides are false. So when one of the sides is false, then the disjunction is true. when one side of the disjunction is true, then the disjunction gets to be true. And when both sides are true, then the disjunction is true. And so the only time it's really failing is when both sides are false. So if we want to draw our picture of this case, then we're going to start with a different box. This time we're using our disjunction box, and we're starting with the same information. I'm going to draw it up as the matrix that we've got in our truth tables, just making it a little bit neater for us. So this is the information that we're feeding into the box. Each of these lines, each of these rows in the table here is a piece of information that we feed into the box. And then what the box does is it shakes around and it yields a value for the compound proposition A or B. So when A is true and B is true, that first line, this disjunction is going to be true. And when A is true and B is false, the disjunction gets to be true because one of the two sides is still true. And when A is false and B is true, then the disjunction gets to be true again. And it's only when both sides fail that the disjunction is false. And this is quite important. Ultimately, you'll need to be able to remember these truth tables. You need to be able to sort of understand them in a way that enables you to recall them very easily and straightforwardly. And the best way to remember this kind of truth table for the disjunction and for the conjunction is to look at the exceptional case. So the exceptional case here is this false case. There's just one case where it's false. If you can remember the case under which the disjunction is false, then you'll have memorized the entire table. If you can remember the special case in the conjunction, then you can do the same thing. There was just one case in the case of the conjunction that was special, and that was when both sides were true. So if you can remember that it's true just when both sides are true, then you can remember the entire truth table because you're going to remember that it's false in all the other situations. Okay, and that gives us our truth table for the disjunction. Okay, so far we've done the not, the and the or. What we've got left is the conditional and the biconditional. I'm going to do the biconditional first, and I'm going to do the conditional last. And the reason I'm going to do the conditional last is because the conditional is probably the most difficult to understand of all of the connectives that we're going to be interested in. And it's probably the one that is ultimately the most philosophically interesting. There are a great many people who've spent in their entire lives trying to understand exactly what that conditional is, exactly what it is to say that if one thing is true, then another thing is true. Because it seems to be really important for a range of things that we do, and yet it can be hard to actually understand what that particular feature of our logical reasoning amounts to. All right, let's start with the biconditional. Right? Remember what I said about the biconditional. The biconditional is this thing, black. This thing, it's the double arrow, which is the two conditionals going in both directions. And what this means is that the two things that we're interested in stand or fall together. So, for instance, consider the following claim. Cats are robots in disguise just when they have robotic legs. So if cats are robots in disguise, then it follows that they have robotic legs. And if they have robotic legs, then it follows that cats are robots in disguise. Similarly, if they don't have robotic legs, then they're not robots in disguise. And if they're not robots in disguise, then they don't have robotic legs. These two claims are always moving together. Okay, so again, what we do is we take our basic claims, we take our possibility space with respect to those basic claims, and we use that to start to understand the possible situations for the more complex compound claim. So we have the claim that cats are robots in disguise is true, and that cats have robotic legs is true, and so on for each of the different combinations that are by now hopefully quite familiar to you. And then what we have is a table for the biconditional. Now what's important about the table for the biconditional is that it's true just when the two sides of the biconditional are agreeing with each other. So when cats are robots in disguise is true and cats have robotic legs is true, then the biconditional says, yes, that's true. And when cats are robots in disguise is false and cats have robotic legs is false, then the biconditional says, yes, that's true, right? So the compound proposition gets to be true. The only time that compound proposition fails is when you have a difference of truth value across the two sides of the proposition. So if one side is true and the other side is false, or vice versa, then that biconditional is going to fail. So we're going to introduce our next box. This time it's the biconditional box. And we're going to feed in the same information to our biconditional box. All right, so we've got inputs of our 4 possibilities, and then this is going to yield outputs of the 4 possibilities for the biconditional statement. So when the biconditional statement, when we feed in TT, when A is true and B is true, then the box churns around and it tells us that the biconditional itself is true. And when we feed in FF, when both sides are false, then the biconditional also gets to be true in that situation, right? Because the 2 things have to stand or fall together, so when they're falling together, then the proposition, this compound proposition, gets to be true. But when they have different truth values, when A is true and B is false, then the biconditional is false. And when A is false and B is true, then the biconditional is false as well. Okay. Again, that's complicated and messy to draw, so we're going to simplify it into this truth table. And this is the truth table for the biconditional. And what we have here, again, the basic propositions and all of the possible options for those basic propositions, and then all of the possible options for the compound proposition in relation to those basic propositions. All right, so that gives us not, and it gives us and, it gives us or, and it gives us just when, or just in case, or if and only if, or the biconditional, in other words. What we need to do now is have a look at the conditional. And the conditional claim is quite difficult. And the conditional claim is difficult because there are certain aspects of its truth table, certain aspects of the way that this conditional box works that don't entirely reflect the things that we might think about the if-then statement in English. And it's very interesting to think carefully about what the differences might be between the English statement and what the differences might be between the logical connection, this arrow that we're interested in. For now, what I'm going to try to focus on is the thing that this arrow gets right. And it's because of the thing that the arrow gets right that we tend to use it when we're developing logical reasoning that models what we're doing in English. Okay. I'm going to build up the conditional step by step. I'm going to start with the easy aspects of the conditional, and then we're going to look at the harder aspects of the conditional. So consider the following conditional statement. If cats are robots in disguise, then they have robotic legs. Now basically what a conditional tells you, and this is the sort of key thing to understand about a conditional, is that it says that if the first thing holds, if you have the first thing, which is the thing on the left-hand side of that if-then statement, if you have the first thing, then you have to have the second thing, right? So if you've got the first thing, then you have to have the second thing. Right? That's what the conditional is saying. So if cats are robots in disguise, then they have to have robotic legs. They're sort of being robots in disguise forces them to have robotic legs if this conditional statement is true. So what we can see is that we're going to be able to understand when this conditional statement is false quite straightforwardly. If the conditional statement is telling us that when you've got the first thing, then you have to have the second thing, then what happens when you've got the first thing and you don't have the second thing? Well, it seems like the conditional is actually failing. It seems like the conditional is false. So, for instance, consider this conditional again. If cats are robots in disguise, then they have robotic legs. Suppose that cats are robots in disguise, but they don't have robotic legs, right? Suppose that that's how the world, as a matter of fact, is. Then it would seem that this conditional statement is true. It's just not the case that if cats are robots in disguise, then they have robotic legs, because there are all of these cats roaming around the world that are robots in disguise that don't have robotic legs. What kind of legs they have doesn't really matter. What's important is that we can imagine a situation in which this conditional is failing, and that conditional is failing when you've got the first thing and you don't have the second thing. Now, the important thing to understand about the conditional is that is the only situation in which this conditional fails. There's only one way to make a conditional false, and that's to have the first thing and to not have the second thing. When you've got the first thing and you don't have the second thing, the conditional breaks. Every other situation, anything else you can imagine, is going to leave the conditional intact. And it's that aspect of the conditional which can be quite counterintuitive. So we'll go through that a little bit carefully. All right, but first of all, we can start to build up our truth table for our conditional statement. So again, what we've got here, we've got all the possibilities. We've got the possible situations under which, possible situations for cats are robots in disguise, and we've got the possible situations for cats have robotic legs. So when cats are robots in disguise is true and cats have robotic legs is true, then we've got some value for our conditional statement and so on. And what we've just said about the conditional is that it fails when you've got the first thing and you don't have the second thing. So if we have a look at the table, that failure is happening in this second line. In this second line, we're seeing that cats are robots in disguise, right? So the first thing is true, the left-hand side of that conditional is true, but cats have robotic legs is false, so the right-hand side of the conditional is false, so the conditional itself is failing. Okay, that gives us the first aspect of the truth table. Now what we've got to do is we've got to think about these other three rows. What do we say about the conditional when both sides are true? What do we say about the conditional when the left-hand side is false and the right-hand side is true? And what do we say about the conditional when the left-hand side is false and the right-hand side is false? Those are the three cases that we have to deal with. Okay, what we're going to do is we're going to deal with the easiest of these three cases, which is this top case. So suppose that cats are robots in disguise and they have robotic legs, right? Suppose that that is how the world, as a matter of fact, is. You get a cat, you look at it, you realize that it's a robot in disguise, you check out its legs, and you find out that it's got robotic legs. And now consider the conditional claim, if cats are robots in disguise, then they have robotic legs. Is that conditional claim true when cats are robots in disguise and, as a matter of fact, they all have robotic legs? Well, it would seem to be the case that the conditional is true. You've got the first thing, namely that cats are robots in disguise, and you've got the second thing, and so that conditional claim, which tells you that when you've got the first thing, you have to have the second thing, seems to be being satisfied. It seems to be true. So what we can do is we can specify this first line in the truth table as being true. So that gives us half of the truth table. The rest of the truth table involves understanding these bottom two rows, and this is where things get a little bit tricky. So let's take a look at these last two rows. All right, in order to understand what's going on with these last two rows, we have to remember what it is that a conditional is telling us. It's telling us that if you have the first thing, then you have to have the second thing. And what I want you to do is I want you to imagine that this is the only situation under which this conditional fails, or any conditional fails, which is, as a matter of fact, the case, right? The only way to make a conditional false is if you've got the first thing and you don't have the second thing. So let's look at these last two situations. Let's take a look at this first situation first. So this is the case where cats are robots in disguise is false, but they do, as a matter of fact, have robotic legs. Now the key thing to ask ourselves is, do we have the first thing? So remember the first thing here, which is the first part of that conditional statement, is that cats are robots in disguise. If we have the first thing, then we can work out whether we've got the second thing and thus work out whether the conditional claim is false. But we don't even have the first thing. Because we don't have the first thing, here's something we do know. We do know that the conditional claim is not false. As I said, there's only one situation under which the conditional claim is false. That's when you have the first thing and you don't have the second thing. So if you don't even have the first thing, then you just don't have that situation where you have the first thing and you don't have the second thing. Which is to say that when you don't have the first thing, the conditional claim is not false. Now, what does it mean to say that something is not false? Well, here's a very natural thing to think. Natural thing to think is when something is not false, that's just another way of saying that it's true, right? So if we say that when we don't have the first thing, that this conditional claim is not false, because as I've said, there's only one way to make the conditional false. You have to have the first thing and then get rid of the second thing or not have the second thing. So when you don't even have the first thing, the conditional claim is not false. If not being false just means being true, then it follows that the conditional claim in this situation is true. So what that means is that if we come to our truth table at last, we have a look at these last two rows, what we can see is that in both of these cases, we don't have the first thing. So we just fail to have that first thing. And because we don't have the first thing, we don't hit the situation which falsifies the conditional. We don't have any way to make the conditional false. Under the assumption that if something's not false, then it's true, it follows that the conditional is true in these last two situations. Now, I'm inclined to be very worried about what's going on in this kind of truth table. This is the standard truth table for the conditional statement inside propositional logic and indeed inside logical reasoning and wherever logic shows up. So the computer that you no doubt use makes use of a similar kind of logical reasoning, and it's going to be using this kind of conditional statement in order to do that reasoning. Why do we use this conditional statement? We use this conditional statement because it gets this bit right. It tells us the conditions under which the conditional is false. Namely, when we've got the first thing, we don't have the second thing. So it seems to get that right. What's a little bit more questionable is what it says about these last two rows. And I think that there are sort of two potential concerns that you might have with these last two rows. And both of them are related. The first one is when you don't have the first thing, when you don't have the fact that cats are robots in disguise, that's just not known, you just don't have that aspect of the conditional, it doesn't immediately follow that the conditional should be true. You might think that rather what should follow is that we just don't know what the value of the conditional is. That we shouldn't conclude it's true here, we should rather think something like we just don't know, or it's unknown, or the conditional is unspecified in that situation. And that's a very tempting thought. And what that tempting thought does is really challenge that sort of natural assumption that I put forward a moment ago. And that natural assumption was something like the following: if something is not false, then it follows that it's true. You might think that that's just not the case. Something can fail to be false and yet also fail to be true. How can that be? Well, something could be not false and not true either because it's unknown or indeterminate or unspecified or some third parameter that we actually haven't factored into the picture that we're working with. The assumption that's sort of operating here is the assumption of bivalence. And what bivalence is the assumption that every proposition in our language is either true or false and nothing else. There are no other options. And the concept of bivalence is sort of at the heart of the propositional logic that you're working with. And many philosophers have found the concept of bivalence since at least the time of Aristotle to be potentially worrying and something that we might want to give up. If we give up the concept of bivalence, however, we have the capacity, at least potentially, to say something else about the conditional here. But if we give it up, then we're potentially giving up something that a lot of people think is a sort of core founding assumption of the way that our world works, namely that every proposition is either true or false. You don't have propositions that sort of just fail to get specified with respect to their truth or falsity. Okay, what we're going to do in this course is we're just going to assume this principle of bivalence. We're going to assume that every proposition is either true or false. And because we can see that the conditional is not false in these last two cases, we're going to accept that it is in fact true in those two cases, and that this is the acceptable and correct truth table for the conditional statement inside logic. There's a whole branch of logic which is devoted to try and work out whether that is a plausible thing to say, whether that assumption is plausible, whether we should think of the conditional in these terms. If you go on with logic, you'll have the opportunity to look at some of those issues. All right, but for now, we're just going to fall back to this, which is the standard truth table for the conditional statement. Again, in order to understand and remember this truth table, try and focus on the exceptional case. And the exceptional case is this second row, which is the only situation under which the conditional is false. So it's false when you've got the first thing and you don't have the second thing. So if you can remember that, namely that the conditional is false when the left-hand side is true and the right-hand side is false, then you can remember the rest of the truth table because it's just true in all the other situations. Okay. The truth tables represent the semantics of our language, of our basic propositional language. What the semantics that we've offered does is give you an account of what each of the compound propositions are going to be, what their truth values are going to be, with respect to the basic propositions that we've entered into the picture. Now, what I'll be talking about in the next lecture is some further aspects of the semantics. I'll give you a little bit of a recap of how the semantics works, and I'll pull it together with the syntax. But also what we're going to look at is how that semantics can then help us to do better or more precise translations when we're moving from English into the propositional logic. Because there are certain cases and certain situations that can be somewhat difficult to understand, or at least difficult to translate when you're moving from English into this language. But if you focus in a little bit more clearly on the nature of the things that we're sort of translating the English into, namely the conditional or the and or the or, we sort of focus in on the semantic understanding, that's going to give us a range of heuristic tools for better translating out from the English. Okay, until then, enjoy your practice with truth tables in the tutorials. Thanks.